Welcome, I'm Bijou Smith and I do some tutoring and I'm going through these NCEA exam papers. The purpose of this is to show you how long it takes for a competent student, not exceptionally bright student, to sit these exams so that you have a reasonable idea of how much time you should be demanding for these exams. Most of my videos I do a bit of extra teaching for pedagogy, so it takes a little bit longer. Also, if I see that I've made a mistake, I want to check it and maybe find the error that I made and correct it, which all sucks up a whole lot of time in your exams. And I think schools and the NZQA should allow students ample time for doing that, to fix their mistakes. Otherwise, this is just a very artificial process, and it's serving the interests of these bureaucrats more than the interests of the students. Students need to have time to sit these exams without stress, because we're testing really the efficiency and quality of the school system, not each student themselves. If you want to have entrance exams for students into university courses and all that, that's fine. You can use these things for that. But if a student really wants to get into a university course, they should just be allowed to keep on sitting the entry requirements until they pass, and then they're fit, even if it takes them 10 years. That would be my philosophy. If they don't want to wait 10 years to pass the entrance qualifications, well then they should probably think about doing something else, right? So that's the political statement. Let's have a look at this. I haven't looked at electricity NCEA level for a long time. That's why I'm doing these things, because I've been working in universities and doing my macroeconomics research and various other things, quantum mechanics. And so I've just recently, this year, come back to tutoring. It's actually 2023, of course, but I'm looking at this past exam paper. So I think this is a good simulation of a competent student sitting these exams. And because I mostly do physics or quantum mechanics and macroeconomics modeling, dynamical systems, the AC circuit stuff, it's all sort of totally confusing to me now, because it's been ages since I did any of this stuff. So what I'm going to use is I've got the resources for this. You can check these out at the NZQA website. Got the achievement standard here, so I've got my basic relationships, capacitors, whatever, transformers, AC circuits, that sort of thing. So anyway, let's see how this goes. Show the reactance of the capacitor is blah blah blah. So immediately I totally forget reactance of the capacitor. It's got to be X. Where is it? XC, 1 over omega C. Yeah, that makes sense. Higher the capacitor, smaller the reactance. So I just go XC equals 1 over the frequency times C, and the frequency in this particular circuit is 50 Hertz. And the capacitance is 54 microfarad. So it'll be 1 over 50 times 54 times 10 to the minus 6. Radio, so let's have a look at this. I'll shrink this down a bit. I was doing a previous exercises before, so plug that into your calculator. .370.3 ohms, but we can only really keep 3 significant figures. Calculate the circuit current. Okay. All right, so already I think I'm stuck. I think well, just from building up charge on a capacitor in a static DC circuit, it goes like that with time. And so for an AC circuit, I guess it's going to go like this. It going to oscillate the current across the capacitor with time, but the current from the voltage supply or through the resistor is going to start at whatever peak and oscillate like that. So I think if you look at that, it's 180 degrees out of phase. So on a phasal diagram, where you're going around the circle is whatever quantity you're measuring. Whatever. Yeah, anyway, I think so. If the resistance starts off here, current through the resistor, let's say, and I think the capacitor will be down here, 180 degrees out of phase. So I think that means the resistance of the it'll be a voltage drop across both, but I think that means the capacitance is minus I over omega c, because it's minus I on the phasor diagram. Anyway, doesn't really matter, because the combined impedance is going to be the magnitude of the impedances for each, the resistor plus the capacitor squared. It's like Pythagoras, right? The total here is going to be the total Z. It's like we're adding two vectors. I'm going to square root that to get the modulus. And then I think maybe I should use the formula sheet here. Whatever the voltage is, V max, it's like V equals IR, but the resistance in an AC circuit is replaced by the total impedance here. So that's what you would use. V equals current times impedance. So current in the circuit, the AC magnitude of the current, say call it max, will be V max over does it mean at t equals 0? I don't know. I'll assume the maximum current. Bit ambiguous, isn't it? So square root of 36 squared plus 370 squared. V is 25. Oh, 6.7 amps. That's two significant figures. That's all we're allowed, right? I know, 3. Guess we're allowed 3. 6, 7, 2. Hey, that's 25. Calculate the phase difference between supply voltage and the circuit current for the circuit shown on that. Supply voltage. Oh yeah, supply voltage and the circuit current. Right. Well, I don't know. Let's just say the current is some function of time. It's a sinusoid, so like I naught e to the I omega t as a phasor, right? So V equals current times the impedance So it'll be current, whatever it is. It could be some delta here, some phase shift at the beginning, but that'll be equal to the combined impedance. So, sorry, yeah, we'll just call it Z. Okay, I might run out of space here. Okay, so that's the current as a function of time times R. Plus, well, notice before that the current is 180 degrees out of phase. Sorry, 90 degrees. Did I say 180 before? I mean 90. Okay. Okay, well, let's just call that the complex number. Let's call it V naught e to the I phi of t, say. Okay, and the components of this, so the V real and imaginary, let's call them Vx and Vy. It's like imaginary, call it the y-axis, real, call it the x-axis, just for example. So Vx is going to be I naught times R, and the imaginary part will be I naught minus I naught over omega c, right? Okay, so we can take the I naught outside, I guess. So that factors that out. And then we've got so I don't know, can I sketch it on here? Say that's at R, and we don't care about the initial angle, we just want the difference between them, the difference, phase difference. So this is omega c here. That'll be the relationship, sorry, 1 over omega c. So the total z will have a magnitude of well, call that theta, right? So cosine of theta, I think it's phi, the way I've defined it here, phi for the thing, for the voltage. So it'll be R over the hypotenuse of this triangle here. 1 over omega squared, c squared. Okay, that was multiplying I. So it's I naught e to the I omega t times, I need some space perhaps. Actually, probably a competent student would be much faster at this because they'd have been practicing all this. So I'm trying to combine the Vx plus IVy into a polar form of a magnitude of the voltage times e to the I times some angle. I guess I'll call it phi t, cosine phi. So yeah. So the magnitude was just the square root thing. So clearly we don't care about the magnitude. This just equals the magnitude of the voltage times e to the I omega plus phi times t, where phi is a constant, and that's the phase angle difference. Obviously, if we just put delta equals 0 there as a reference angle, then it's going to be inverse cosine of r over square root squared plus 1 over omega c squared. And I guess we better calculate that since we've got the numbers right. Sheesh. Putting them in. Let me just define these things. 36. Let's call it W for omega. 54 exponential minus 6. And then we want inverse cosine, which is arc cos or a cos. R divided by square root r squared plus 1 over brackets W squared times C squared. Probably just W times C squared. I guess I could multiply that by 180 over pi to get degrees. 1.47 radians, or 84.4 degrees. Where am I? Three significant figures. Good. Alright. Oh, yeah, hang on. So, the idea of resonance was that when the driving frequency, say the supply frequency, is tuned to some natural resonant frequency, then the current, in other words, the voltage and the current, I guess. But let's just look at the maximum current, the amplitude of the current. So not oscillating. So this is not time here. This is the frequency of the driving circuit, power supply frequency. Frequency of the supply. It'll if you're not at the resonance, the current will be sort of a low value. But then at resonance, it peaks to a high value like that. It might look actually kind of, it's a Lorentzian shape, so it kind of looks like that. I can't draw it. Anyway, that would be the resonant frequency here. So the idea behind that is the basically the Ohm's law for the circuits again. So we get I maximum proportional to 1 over the impedance. So it'll be 1 over, remember the impedance is complex number, so it'll be Z equals, so stick a, okay, we better make an assumption here, whether it's a parallel or whatever. Yeah. All these little things you don't have to do in an exam. Anyway, put an L in series. That's what we'll do for a start. In series, then the resistance will just be the sum. There's the total impedance will be the sum of the impedances, and for yeah, so XR plus X the inductor plus X the capacitor, or Z's if you like. Yeah, so the impedance for the capacitor, I think, is I omega L. But as a complex number, then the imaginary part of the phasor for the impedance Z will be an omega L and a minus I for the capacitor. Remember, the capacitor was minus I over omega C. I don't think that's in the formula sheet, but it should be. Okay, then squared. Square all that because we're taking the modulus. So we can minimize, these are positive values. So the best we can hope for to minimize denominator implies the maximize the current. Smaller denominators, bigger value, means we need omega L equal to minus omega C, so that this thing goes to 0. I mean, it can't be negative, so the smallest, and R squared can't be negative. So the absolute smallest we can get is that, which implies that omega squared should be 1 over LC, I believe, and that so omega equals the 1 over the square root of LC, I believe. I should check that out. Check that later. That's a math kind of explanation, not so much a physics explanation. Physics explanation is that the capacitor is like a spring, the inductor is like a mass. It's an inertia. It sort of it operates to halt the flow of current through itself. And so you've got a mass on a spring, and you know, if you just touch a mass on a spring, it'll start vibrating at a particular frequency. That frequency that it vibrates at will be this one here. And although the LRC circuit here is not a spring and a mass, it turns out that the equations of motion for the current are exactly the same for a damped oscillator or spring. All right, on to electromagnetism. Guess I should make a distinction above. That's the resonant frequency that we want. It's not necessarily the frequency of the supply. So for this inductor, we've got a DC circuit here, and so it's a different behavior. The thing that you'll probably be thinking of is that the voltage starts at the V naught, and it's going to be constant, but the voltage across the inductor will definitely start at V naught. But the inductor voltage, so a voltage across an inductor is only there if there's a current to react against it. And the voltage is a reaction against any change in the current. So it's proportional to change in the current. So as soon as the current reaches the peak, constant, so if we draw the current here, obviously it takes a while to get electrons moving, at least a few nanoseconds or whatever. So the current starts at 0, but then it will reach some sort of maximum. I guess we could call it max. And it goes something like that, right? Actually, if we had sort of infinite precision kind of stuff, it wouldn't reach a maximum until t equals infinity. So we could call it I infinity. So the actual current would go up, and in practice it'll reach this level because of noise. It'll always sort of stabilize. But that means the inductor voltage, once here the rate of change of the current here is going to go to 0 as time approaches infinity. So as time approaches infinity, the voltage across the inductor is going to go to 0. So it goes something like that. And time constants. Do they have this in the formula sheet? They probably do, but why don't I just why don't I just repeat the theory? Okay, so you can subtract this from the time it takes to do the exam, because you probably don't have to, oops, you have to repeat this all yourself. But what we've got is a voltage, and then I guess it's the other way around, isn't it? It doesn't matter. And then you've got a resistor, and then an inductor, and then so using the loop rule, which is really conservation of energy when you think about it, we've got the voltage. We start with the voltage going up here, and then we go down IR for the resistor, and then we also go down for the inductor by minus L di by dt, depends on the rate of change of the current. And of course we've gone around a loop here, so that's 0. I can rearrange that, divide by L, and switch a few signs and that sort of stuff around. So it'll be R over L equals V. Now this is a typical differential equation with sort of a characteristic polynomial that looks like this in the case when the voltage is 0, and so it indicates a characteristic value of minus R over L. So you just say lambda is the derivative for these linear differential equations. Lambda is the derivative. You send the actual function I just to 1, and then you set the driving force, or the inhomogeneous function, to 0, and then you take a guess from that lambda. You say that I is equal to some amplitude E to the lambda t plus some residual, call it B, IA, and we've got to determine these constants. IA for a current, lambda for a time constant, and B, lambda is 1 over the time constant. So it's actually E to the t over the time constant. So it means lambda equals 1 over the time constant. Anyway, the idea is to plug this back into the differential equation here. When we do that, di by dt is lambda lambda t. We've already solved for lambda, right? Using the trick, using our background knowledge. But suppose you didn't know that. Maybe I should do that. This will take a bit longer then. IB is a constant of integration, so when you differentiate that, it goes to 0. So all we've got left is L over R times IA e to lambda t plus IB will be equal to, oh sorry, this was voltage over the inductance. We divided everything by L here to get rid of the L on the derivative. So that's V over L. All right. You do with that. You need some initial conditions. So at t equals 0, V equals V naught, the supply voltage. And I guess that's always going to be V naught over there. I guess we could say the current at time t equals 0 is equal to 0, right? That's one initial condition. There's no current to begin with. So that means we plug that in. This is t equals 0, and here we get IA plus IB equals 0. So that implies IB at least is equal to negative IA. Okay, so that eliminates one of those constants. Okay, so then the current as a function of time will be equal to just IA e to the minus. Okay, maybe we don't want to assume we did this fancy stuff here, this theory of differential equations. Sorry, it's going to be -1, right? Because b was negative a. The other condition is at infinity, the current will be equal to a maximum, or I infinity, which is just going to be given when basically the inductor voltage drop goes to 0, and so it will just be V equals IR for the resistor, so the current will be V over R, or the voltage supply divided by R. But we know V at t equals infinity, it's going to have to be given, it can't explode to infinity, right? It means lambda is going to have to be negative, otherwise e to the lambda t would blow up to infinity, and so e to the lambda t goes to 0 because it's a negative, e to the negative infinity. Let's just write it out. Okay, and that means the current at infinity will be just equal to IA times -1, and that has to be equal to V naught over R. So that implies that IA must be equal to negative V naught over R. Okay, so then we've got negative V naught over R e to the lambda t minus 1. I guess we write it like that. Okay. I guess if we put that back into the differential equation, okay, call this maybe equation 1. Okay, 1 at t equals 0 would give us lambda times negative V naught over R plus R over L negative V naught over R plus V naught over R. Remember, we're putting t equals 0 in here, so the exponential goes to 1. Must be equal to V naught over L. So that goes to 0. Yeah, so lambda has got to be equal to V naught over L, and we multiply by the reciprocal of that, so it would be negative R over V naught, and so that will just be equal to negative R over L. Okay, great, because that's what we wanted from our, if we were mathematicians, our characteristic equation here for that linear differential equation. All right, so cool. That's after all that differential equation math, we get why don't we just put a negative out the front here and change this to a positive, so it'll be V naught over R, and we can bring the negative sign inside the bracket, so instead of exponential plus 1 will be 1 minus the exponential minus 1 will be 1 minus the exponential, and lambda is negative R over L. Alright, that means the time constant is equal to L over R. So that means I drops to what was the question again? Calculate the circuit current after 2 time constants. I guess we can write this in here, V0 over R 1 minus e to the negative R t over L. Goodness knows if this was in your exam paper or not, but hopefully it is in your formula sheet. Or you could just say the time constant for an LRC circuit, sorry, for an RL circuit, DC circuit, is just equal to RL over R. Geez, did I get that right? Dimensional analysis would sort it out if I knew my dimensions offhand. So 2 time constants. Basically, if T equals 2L over R, then the current will be at T equals 2L over R, two time constants. Then the current will be V over R, 1 minus e to the power of, well, you can see it'll just be a 2, e to the minus 2. Now we've got to put in the numbers, I guess. 12, 22, 1 minus 1 over e squared. E is the same as exp 1 on your calculator, I guess, or there might be just a button called E. Half divided 22. I guess I better put 1 over there. Let's just check that it's the same as minus 2. Sweet. 4, 7. How many significant figures are we allowed? 3, 4, 7, 2. It's all SI units. 3 significant figures. Capital A for amps. That'll be what the current gets to after 2 time constants. There's a time constant here where it's at 1 minus 1 over e of the initial value, and then another time constant here, 2 TC, where it's gone up to 1 minus 1 over e squared. It's getting closer and closer to 1 the more time constants we go up. 3 time constants, it'll be even closer and closer and closer. Okay, good. So the pure inductor, so the resistance of the inductor is going to be 0 here. Obviously, usually inductor has you usually model it, a single inductor as an inductor plus a little bit of resistor. But you know, you can always include that resistance onto a separate circuit resistance. Anyway, pure inductor, once the current is steady, so di by dt is equal to 0, that's a steady current, which means the voltage across the inductor, which is proportional to the rate of change of the current through the inductor, we should say, really. Current through the inductor is going to be equal to 0, so it's equal to 0 volts. And across the resistor, it'll just be V0, which is, I think I had it about, was it 12 or 22, 20, 12? 12 volts. Once the current has reached a steady value, the switch is open. Wait a minute. There's a switch there. current was in that direction, but it's going to go to 0. So in this case, we're at some sort of steady state, and then it drops off. And of course it's series, so that's the same current through the inductor and the thing. So the rate of change, the slope of that is negative. So the rate of change of the current through the inductor is negative. The voltage is negative L di by dt. And so the average voltage across the inductor, that is, will just be the final minus initial, the sort of average of the two. So it'll just be minus L. And then what's an average rate of change? You just go from the initial to the final value here at whatever, infinity. Okay, but actually it's not infinity. It's 2.5 times 10 to minus 2 seconds, 0.0025 seconds. Let's call that 0 for now. So the average would just be the green, the slope of the green line there. It starts off rapid and then goes to, and then slows down. You can see the slope is changing if I do the proper curve, but the average would just be going from the initial to the final state. So that'll be I max divided by the time interval. So final minus initial. I'm going to be rigorous about it. Final minus initial divided by final minus initial time. Okay. 1.6 for the inductance SI units, I think, is Henry's. And then okay, so the current, what was the current? Oh yeah, well Imax is going to be Imax is going to be equal to just V over R, which is 12 over 22. Right, 5454 recurring, right? Okay, it's just a calculated time. Let's just put in the number, put in the ratio, since we can do it exactly, at least up to that point, divided by the time period. Is that right? 0025, 10 to the minus 2, 1, 2. Oh no, that's just a 1 0 there. We started off at 2.5. We'll go back two decimal places. Here as well. Sorry about that. Yep. Cool. Okay. What? Should be multiplication there. 36.7 volts to 3 significant figures. But did we want the current? Oh no, that's the average voltage. And the direction, so normally it's a voltage drop going down, that'd be negative. But in this case, it's a increase. Well, it's going in the opposite direction, if you like, because it's discharging. So it's kind of like it's going in the reverse direction. How do we say that direction of the induced voltage across the inductor? This opposite to the current flow. Okay, can we go left to right? Okay, so it's positive on the right hand side. So, oh yeah, so wait a minute. I guess I got the polarity of my thing around the wrong way. So in fact the current is not that way, it's going around this way. And so normally the voltage would drop, go from A to B. It would be a drop from A to B. But this is an increase, increase from A to B. V from A to B is positive 36.7 is one way to put it. While it's charging up, that would be negative. It'd be a loss through the inductance, because the rate of change of current is positive in that case, which means that's positive, which means the voltage is negative. The drop in voltage across the inductor. We should call these voltages always delta, I guess. Okay, I think that's all for that one. Time for a cup of tea. Right, well, if this resistor is 2 times higher, then time constant, which was L over R, is going to be half of the old time constant. It's proportional to 1 over the resistance. T2, T1 here, I guess. 2 that gets confused with squaring. Half the previous. So in terms of the current build-up then, building up to maximum current, and whatever this was here, 1 over E, was it 30% or something like that? So this would be the new time constant. Let's call it prime. Usually that's a symbol. And that'll be half of the old one. So the old one would have been built up here. So the previous original circuit, 22 ohms, I guess. This will be 44 ohms. Okay, so L over 2R. R prime is the new resistance. Call that R prime. This would be R. Now, size of the maximum current drawn from the circuit. Yeah, so this maximum might change too. So in fact I've kind of drawn it incorrectly, and you might be able to go back and find out what that was. Do we write it down? Or maximum current would occur at t equals infinity, and then V over R. So we had, let's write that down. It's still true that that's v naught over r, but it's r prime now. 1 minus e to the negative t over tau prime. And here's a short way of doing that. That approach is v naught over r prime. 1 minus, now as t approaches infinity, e to the negative infinity, remember e to the x looks like this. And so negative infinity is way off in this direction here, so it's going to go to 0. And so that's going to be just v naught over r prime, which is equal to v naught over 2r. So therefore the maximum current is reduced by half. Reduced by half the previous. So what should I draw? I should update my diagram there. So previous one would be I max there, or I infinity, and the new one will be I infinity halfway there. And so it'll go up. Okay, let's try these time constants. I don't know. 30% at the time constant there. The other one was 30%. It was about here. I don't know. It's a bit hard to draw these, but I think the new one will look like that. The old one, I don't know. It's hard to draw it because of halves and things. I don't know. The old one might look like that. It's a bit hard to estimate whether they overlap or not. There's a difference in scales there. I guess I could exaggerate that. Sorry to do this. Let's say the time constants are really close in like this, so we have a better asymptotic to our prime tau original. So this one, if this one goes up like that, the previous one might have gone up like this. But I don't really know if they cross over here or not. I have to think about that. What else do we have to do? Yeah, time. So we've done the time constant. That was the first thing I did. Size of maximum current. Energy stored in the inductor once the current is steady. Okay. Just remember the energy for the capacitor is something like half capacitor times the Q value squared. Energy for an inductor is like half mass times velocity squared. Now, is that the current squared or is it the voltage or whatever? So let's go to our relationships here, since I don't want to look it up. Half Li squared, indeed. It's analogous to motion of a particle with mass L and velocity like the electric current. Velocity of a charge. So current is steady. So the energy stored, I guess that's inductor L, and the inductor at t equals infinity will be equal to half L I infinity squared. Don't get scared by I infinity. That's just the maximum that it tends towards. Which is a half L. We calculated it up here, V naught over 2R. But it will be 2R prime. So, put in the numbers. Forget them already. 1.6 Henry. And 12, was it? Geez, 12, yeah. Oh, you better square that. Don't forget. 12 over 88, 2 times the new resistance, plug that into the calculator. Ah, it's supposed to be a half. 0.5 times 1.6 times something squared. Go back and fill in the bracket. 12 divided by 88. Now, if it's all SI units, which I think it is, it should be 0.15 joules. I guess we can do three significant figures. 0.149 joules. Hang on. 0.149. Let's do three significant figures. The 1, the 4, and the 9. You can write equals there because you're telling what the precision is. If you don't say the precision, you'd have to write it approximately equals, which is very vague. It's better to state the digits and the precision is better. Then you can say equal to. Although some people might technically still go approximately equal to. But what you're saying is that the energy up to 3 decimal places is equal to this. Okay, I think that's all for that one. Energy. Yep. Let's say we've done that. And I'll take a tea break and have a look at DC circuits. It's a bit disappointing though that electromagnetism, just want to make a political comment here, has been reduced to these inductors, circuits, and blah blah blah. Where's all the electric and magnetic fields and everything? Surely at level 3 you would be doing that. Anyway, I'm going to pause the video here, but I'll restart it smoothly in a second, so you won't notice. Okay, this one we've got meters and meters here, so just check the SI units. And then we've got capacitance. Actually, maybe I won't do that. Maybe I will imagine. Okay, look up the formula sheet, supposedly, because I don't know what the capacitance of a capacitor is. Where is it? Here we go. Epsilon A of D. So suppose I'm going to make a. Actually, this is the one time I might make a deliberate mistake. But you're allowed to do this. Okay, supposing I do this, then it's 1 times 0.16 divided by 10 to the minus 3. So that's the same as multiplying by 1,000. So it'll be 1, 2, 3. So it'll be 160 farad. That's a huge freaking capacitance. So, you know, capacitance is normally of normal devices are around nano to micros. So you say, oh, what did I do wrong here? Now, that's because I was looking up the NCEA. So I can erase that from my exam because I know the answer that I'm supposed to get. So the trick here is actually I should look at the formula sheet for the actual exam. So I think this is the formula sheet that you get given. Okay, so here's the capacitance formula, and the two epsilons might obviously jog your memory. One is the epsilon naught, which is 8.85 10 to the minus 12. So that's what we've got to do. Let's stick in that thing here. Capacitance equals epsilon naught times the relative permittivity, that's ER, and then A over D. So it'll be 8.85 times 10 to the what is it? Minus 12 times 1 times 0.16 all over 10 to the minus 3. Okay, so 8.85 exponential minus 12 times, well, just times 160, because divide by 10 to the minus 3 same as multiply by 1,000. So 1.16 goes up to 160. 1.42 times 10 to the 9 to minus 9 farads to 3 significant figures. Energy stored in the capacitor. So it's something to do with Q's and V's and all that. A half QV. Well, when it's fully charged, we need to know what V is. Fully charged will be at 9 volts. Fully charged implies V equals 9 volts. And so the energy is equal to a half Q. Oh, wait a minute. We want the other formula because we don't know what the charge is. Q equals CV. Q equals CV. So the energy equals half CV squared. Stick the CV into here. Okay, so half times 1.42 times 10 to the minus 9 times 81. Calculator, where are you? 0.5, 1.42 exponential negative 9, 81, 5.75 10 to the negative 8 joules. Not too much of a wallop. Describe the effect on the energy stored in the capacitor when a sheet of mica R. Okay. ER prime goes to 7.0, which equals 7 times the original for air, which implies C prime which is proportional to the relative permittivity, increases 7 times, which implies the energy is proportional to the capacitance, and the voltage won't change, but V is still 9 volt, so the energy in the capacitor, which is proportional to the capacitance times V squared, increases 7 times as well. Sorry, I'm losing my... Here we don't have an implies there. V is still 9V, just a statement which implies. We don't need the implies because I've written so. Okay. I think that's all we need for that. Okay, so let me spell a warning here. Do not. And this is probably the most annoying thing about the electromagnetism. Do not confuse E as a vector with E energy. This is the field, it's a vector. This is the energy, and they're totally not the same thing. So, let me... Now, I think a reason why you might accidentally confuse them is, yeah, so if you look at the website, I shouldn't be showing you my bookmarks. Yeah, so here, this is the electric field, should be a vector. This is the energy, it's fine. This is the energy. That's fine. So yeah, the only one that's the vector is that should be the vector is the one between the voltage and the distance. So it's the distance that you go along, the direction of the d, that determines the direction of a vector field. Okay, so the proper relationship is that the field is the rate of change of the voltage in a particular direction. In other words, it's a gradient of the voltage. Three-dimensional derivatives, you'd write it as a gradient, three-dimensional derivative. Yeah, but the E is equal to Q times the change in the voltage in any direction. So that's it's the change in voltage that you move charge through. Take the charge from here to around about all over the place and change it, take it to here, and then the difference in the voltage along the straight line path will determine the change in energy, no matter where you move, no matter how you get from A to B. So you could say voltage from A to B. So those are totally different things, but they use the symbol E for both of them, capital E. So it should be a vector on the field. Energy is completely different quantity. What's the field's volts per meter? What's the energy? Volts per coulomb. So, sorry. What's the potential volts per coulomb? What's the energy? Just joules. Energy will be coulomb volts, if you like. Got the arrow in the wrong way. Okay, anyway, the charge on the plates. The plates are electrically isolated. Isolation implies no change in the charge on the plates. Q, so the same. Yeah. Okay, but if we increase the separation, then C equals epsilon A over D. Well, if we increase the denominator, it will decrease. Okay. So what does that do to the voltage? Well, I don't know which is the formula in the sheet there. So Q equals CV, but the Q equals to CV. So therefore, if C decreases and Q is the same, okay, so Q is the same, so C decreases, then the voltage must increase. Voltage must increase. Now, it doesn't mean anything to do with the electric field. This could be the same because you increase the distance, you increase the voltage, so the field could be the same. But what's happening here is that the person, imagine pulling the plates apart. This is a plus Q here and a minus Q here, or minus Q negative if you like. Yeah, just call it Q. Just call it Q. A plus Q and a minus Q on the plates. So if you pull those apart, you're pulling charges that are attracting to each other apart. It's going to take some effort. So she did work on the system. So that has to show up in some sort of potential energy, but it's in the electric field, so it's kind of like a spring, but it's invisible because it's in the form of constantly scattering photons between the plates. That's the electrical force, scattering of photons. But they're they're not in the visible wavelength range. If you had spectacles on, you'd see that could see very low energy or very low frequency or very large wavelength radiation, photon radiation, light radiation, then you could see it increase in brightness at that very large wavelength. It's very, very low energy light. You can't see it. That it'd be bright in that region of the spectrum, and so it's the voltage that increases, charge stays the same, so the energy will increase as well. Anyway, so E equals Q, V increases. This is the electrical potential energy, or EPE. Sometimes they write it. That's the explanation. You don't need to explain it, I don't think, but there's some explanation. Yeah, perhaps this is for an excellence endorsement, whereas this is, if you just do this, it's maybe merit, something like that, maybe. Okay, we have to do some parallel. Wow, let me try and go over this. It's probably on the formula sheet. These extra notes. Wait a minute. Let me check the formula sheet. C total equals C1 plus. Oh, that's no good. You don't know which is parallel and which is in series. So I want to go over this in a bit of theory. So basically, what we'll work out here is what happens when the capacitor is series and parallel, because on the formula sheet they're not given, but the formula that we want to use to derive this is Q equals CV, or if you like, V. Okay, so Q equals CV, or V equals Q over C. Either one will do. Okay, but if they're in series, we've got a capacitor here, and then another one here, and then so on, a bunch of others. And so we've got a positive Q, say here, a negative Q here. So that means that the field is from left to right. But there'll be a current flowing across this junction unless the other charge was also negative to repel. So plus Q, minus Q, so on. But on the other side, it'll have to end with a plus Q and a minus Q, obviously. Now the thing about this is there's a voltage V1 here, V2, and so on. So the total voltage is just V total. So what we can say is that the total voltage, which will be equal to the total effective Q divided by the total series capacitance, right, just by this relationship. But that total is made up of the sum of all the individual voltages across all the capacitors. And that's just equal to the sum of the charge on each side of each capacitor, plus or minus, divided by the capacitor. But the charges are all the same. So it's just Q over Ci, summing from I equals 1 to however many capacitors we've got. So we can take the Q outside because it factors out, it's a common factor, and we just get left with 1 over Ci. Now, of course, this will be the total charge Q, so we can cancel that, and we get 1 over the total series, let's call it the series, will be equal to the sum of all the capacitors, but the reciprocals of the sums. So the way to write it for 2 capacitors would be equal to 1 over C1 plus 1 over C2. Alright. Now what about parallel? It's a similar idea, but kind of opposite argument, if you like. So you've got a bunch of capacitors in parallel now in some sort of circuit here. Okay, now what do you know from here to here is the voltages are all the same. But the charges may be different. This could be Q1 plus Q1 minus Q1 plus Q2 minus Q2, Qn minus Qn. But the Qi could be different. Right? So in this case, we could use the formula. We could say the total, this is equivalent to some big capacitor maybe with a total Q on it, plus or minus, which means that that voltage, which is the same, or the Q, so we use, in this case we use total voltage, total charge equals the total capacitance times the total voltage across each of them. Okay, but that's the sum of all of the different charges on each one of them. Okay, and that is the sum of each of the individual capacitors times the voltage across each of them. But because they're in parallel, the voltages are all the same from A to B, VAB. Okay, so V voltage, the change in voltage across all of them is just V from A to B. So that's just equal to the sum of each of the individual capacitors times V total, which factors out of the sum. You can put it outside, and so we get, in other words, this must be equal to this. So V total times the total capacitance must be equal to that, and we can cancel the V, and so we get left with the total parallel is just the sum of the individual capacitors. And so for the two capacitors two of them in parallel like this, C1, C2, parallel, or C total, or total, is just equal to supposed to be in parallel, not series. So if we just had two of them like this in parallel, you could replace this by a circuit with just one capacitor, one overall capacitor for the whole lot. So it's the same. The circuit is the same as this circuit, C total, where C total is just equal to C1 plus C2. Sorry about that. And then with those results there, we know which formula in the formula sheet applies. So let's call that C1 and call that C2. So C2 equals CA plus CB. And just put in brackets what you know, capacitors in parallel add together. So that's 2 plus 6, so that's 8 times 10 to the 2 microfarads. Okay, now C total, 1 over C total is 1 over C1 plus 1 over C2. And you don't have to spell this out, just say capacitors in series. that you know the rule for them. They add as reciprocals. Alright, so that means C total is just, 1 over C1 plus 1 over C2. Okay, so that's 1 over 4.7 times 10 to the 2 plus 1 over C2 was this 8 times 10 to the 2. And that just keep some significant figures here. -2. It should be less than each of them individually. It should be less than 4 and less than 8. Yeah, that's good. So it's about equal to 2.7, you could say 2.75 if you wanted to keep -2 farad. Okay. Oh, microfarads, jeez. Yeah, they look like an enormous capacitance. Capacitances are usually pretty small numbers in SI units. Right. Is that it? Beginning. Calculate the voltage. Ah, hang on. Okay. Total voltage equals 12 volts, which equals V1 capacitor plus V2 capacitor. And run out of space here. Okay. Yeah, so let me insert some space paper here. Exam paper. But when the circuit's fully charged up, right, the charges on these things are going to be the same. If we talk about V2 as a combined capacitor, right, so V total equals Q over C total, right? And sorry, we want to get the capacitance across V1. Or maybe we could write that down. Okay, voltage. Okay, so okay, let's concentrate on what we want. V1 is going to be, okay, remember the formula. V is charge divided by capacitance. So it'll be Q divided by C1. And V2 will be equal to the same charge. They're in series. So the same charge. Q on C1 and the combined thing C2, right? So it's C2, the combination of these the 8 times 10 to the minus 2 farads. I know, it was plus 2, wasn't it? So yeah, plus 2. Did I get that right? Oh no. Oh yeah, that was stupid. 2 microfarads, that's a -6 plus 2, so -4. So it's 1, 2, 3, 4. Man, I was really being stupid there. I forgot the microfarads here. Mu is 10 to the -6. Okay, so that would be 6. Yeah, so -4 here. And that would be well, there'd be 10 to the 2 microfarads. It'll still be 10 to the -4. I think 1, 2, 3, 4. Yeah. All right. I fixed that error. I forgot. I kind of lost my train of thought here. Getting late in the evening. Yeah. So oh yeah. So I didn't finish writing this one. Okay. Okay. Therefore, 12 equals. Can we solve this directly? Q over C1. It's V1 plus V2, right? V1 plus V2 is this. So we know the charge. Okay, so that's equal to Q times 1 over C1 plus 1 over C2, which is equal to Q times 1 over C total, which we just computed. And therefore, V1 is this Q. Oh yeah, so let's just try and do that without computing Q. We don't want to have to bother computing Q. So rearrange this. It means that C total times 12 equals Q. So V1 equals 12 times C total divided by C1. So it's 12 times 2.75 divided by, now just make sure the units are the same, C1. Yeah, it's 4.7, right? We could do the 10 to the 2 microfarads, but it's the same on the top and the bottom, so that'll factor out. So we can just do 12 times 2.75 divided by 4.7. That's as long as I didn't make any mistakes with powers of 10. 7.02 volts. Volts is usually capital V. It's the same symbol as for the units. That's always a bit confusing, right? But you're allowed to write V. Yeah, okay, that's the end of the exam. Anything else? I think that's it. Okay, note how long it took me, but you can subtract off maybe 10-15 minutes from my fluffing around with some of these explanations that you wouldn't need to do in an exam. But that show you roughly how much time you should demand for your exams. Okay, bye for now.